Hello everyone, welcome to the SWAM NPTEL course on Mathematical Geophysics. We continue with module number 8, Data Driven Analysis in Geophysics. This is lecture number 4, Transforms for Geophysical Analysis. In this lecture, we cover the general methods for geophysical data analysis which are related to various transforms. First, we will look at the Laplace transform, next, Z transform, then we will continue with discrete Fourier transform and the properties of discrete Fourier transform and fast Fourier transforms. Finally, we'll look into the various geophysical applications. So let us begin. What is Laplace transform? The Laplace transform is the generalized version of Fourier transform for continuous signals. Later on, we will look at transforms for discrete signals. First, let us see the transform, that is Laplace transform. The Laplace transform is an integral transform and it is used for analyzing linear time invariant systems or LTI systems. Now, this transform is also a linear transformation. It obeys all the rules of linear superposition and linear functions. Basically, the Laplace transform converts a signal which is continuous in time into its Fourier domain, which is complex Fourier domain in S. Here S is a complex number and this complex function of S, x of S, is the transformed function through Laplace transform. Now, x as a function of t is also a complex function. Which means that the functional values of both these functions are complex numbers. Thus, Laplace transform converts a signal into its complex Fourier domain, while Fourier transform converts a signal into its real frequency domain. The Laplace transform solves differential equation and it can be also used in understanding and interpreting the signal in complex domain. This is the notation for Laplace transform. X of S equals L of x of t. L is a symbol representing Laplace transform. The mathematical definition of Laplace transform is given by x of S equals integral 0 to infinity x of t e to the power minus st dt. You can compare this with the Fourier transform where instead of S we would have I omega. Here S is a complex number which is a plus ib. Here a denotes the growth rate or fall rate of the complex exponential. Such that we can write e to the power minus st equals e to the power minus a plus ib t, which is equals to e to the power minus at multiplied by e to the power minus ibt. In this complex exponential, the first part e to power minus at denotes growth or fall of the function as the sign of a is negative or positive. Now, the second part e to power minus ibt represents the oscillatory nature of the function. In Fourier transform, the growth and fall of the function part is not present. While only the oscillatory part is included. Thus, Laplace transform includes the growth and fall part of the function and hence is a generalized version of the Fourier transform. In other words, while Fourier transform is only capable of analyzing periodic functions, Laplace transform is capable of analyzing periodic rise and fall functions. For example, the functions of this category, which are periodic, oscillatory, and also decaying with time. Such type of functions are more suitably analyzed using Laplace transform, while Fourier transform would be more appropriate if the amplitude of this oscillatory function would remain constant. Thus, we look at the more properties of Laplace transform as delineated below. We have discussed that Laplace transform is a linear function, which means the Laplace transform taken for the sum of two functions x and y is equals to the sum of the Laplace transforms. That is, Laplace transform of sum equals sum of Laplace transform. Next, we have the time shifting property, which means the Laplace transform of any shifted signal is equals to exponential multiplied by its transform. By multiplying e to power minus at, the phase of the transform is shifted. This causes the shift in phase of the Laplace transform. Next, we have the frequency shifting property. Now, suppose we multiply e to power at with xt. This changes the frequency of the signal. This is the Laplace transform which is shifted in the complex domain. Thus, if we multiply an exponential function with the original signal, the Laplace transform would be frequency shifted. The next property is about derivative and integration. The Laplace transform of derivatives is given by multiplication in the Laplace domain. Thus, derivative or differentiation in the time domain is equivalent to multiplication in the Laplace domain. Similarly, integration in the time domain is equal to division in the Laplace transform domain. Finally, we come to the convolution property, where the Laplace transform of the convolution of two functions is equal to the product of the two functions in the Laplace transform space. This is also in line with the property of Fourier transform, where the Fourier transform of two convoluted functions equals their multiplication in the Fourier domain. Thus, Laplace transform is a transform used for generalized signals for analyzing in the continuous time domain. Now, we look into the next transform, which is meant for discrete signal. It is called the Z transform. The Z transform is used in signal processing and systems theory to analyze discrete time signals. In geophysical measurements, we have data which is obtained from field measurements or other natural phenomena monitoring which uses discrete time signals. Thus, Z transform is very useful for analyzing such signals. Systems that operate on discrete data need to be analyzed using Z transforms rather than Laplace or Fourier transforms. In fact, the essentiality of Z transform is that it is the discrete counterpart of the Laplace transform. Thus, whatever is the action of Laplace transform on continuous signals, similar is the action of Z transform on discrete signals. Thus, the Z transform converts a discrete time signal given by x of n into a complex function x of z, which is in the Z complex plane. Now, Z is in the Z transformed domain while n is in the real physical domain. N is an integer. The mathematical form of the Z transform is given by this equation number 2, which states x of z, which is the Z transformed function, equals the summation of x of n into z to the power minus n. Now, let us look at the right hand side of this Z transform equation in more detail. We have two parts of the function within the summation sign. One is the signal itself, which is x of n. The other, z to the power minus n, is the basis function. This basis function is similar to the functions which is used in Fourier transform or Laplace transforms, such as e to the power minus I omega or e to the power minus st. These are the basis functions which are multiplied by the signal and integrated or summed over. To understand the Z transform in line with the Laplace transform, we can look into the following analogy. The function x of t in Laplace transform is replaced by x of n in Z transform. While the basis function e to the power minus st in Laplace transform is replaced by z to the power minus n in Z transform. The integral sign is replaced by the summation sign due to the discrete characteristics of the data. Hence, we have the Z transform, which is an analogous transform to Laplace transform. Note that Z is a complex number and can be represented in the Euler notation as r e to the power I theta, which is magnitude r multiplied by e to the power I phase angle theta. Now, let us consider the region of convergence. The idea behind region of convergence is that the Z transform may or may not exist at all domains within the transformed space. Thus, the region in the transformed space where the Z transform is finite is known as the region of convergence. This means that the sum which is expressed in right hand side of equation 2 converges, and thus the region of convergence is defined so. The region of convergence is crucial for determining the stability and behavior of the discrete time systems. Now let us look at the next discrete Fourier transform, which is the discrete version of Fourier transform. We have looked into the continuous version of Fourier transform in previous lecture. This is the transform which is used to analyze discrete signals in the frequency domain. Now, discrete Fourier transform is the most commonly used tool in signal processing, including geophysical applications. Since geophysical instruments sample the analog signals, the data is in discrete form, and the frequency content of this discrete data set is more appropriately obtained using discrete Fourier transform than continuous Fourier transform. The fields of applications are seismic and electromagnetic applications in geophysics. The mathematical representation of the discrete Fourier transform is given in equation number 3. We have the x of n as a discrete signal. Now this discrete signal is made up of capital N samples, where k is the counter and total number of samples is n. Thus, k is the transformed variable which is written on the left hand side. N is the counter for discrete signal x of n in the time domain. Thus, n and k are integers and they are counter for time and frequency domain functions respectively. Thus, we have the basis function given by e to the power minus I 2 pi by n little n k. This is a discrete basis function. Note that we had continuous basis function previously for Laplace transform, Fourier transform as well as Z transform. But in this discrete Fourier transform, the basis function itself is a discrete function. Thus, the resulting transform is capital X of k. The discrete Fourier transform converts the time domain sequence into the Fourier spectral domain sequence as given here, where x of k represents the frequency component of the signal. Note that for k equals to 0, 1, 2, 3, etc., these are the frequencies which are discrete in nature. Let us understand this with the help of this example and diagram. The left-hand side represents a discrete sequence, which is a set of points on the x-axis and the values given on the y-axis. N is the counter and x of n is the discrete function. Now we have for n equals to 11 number of data points which are discrete in nature. Now converting it to the discrete Fourier transform domain, we have k on the x-axis and capital X of k modulus, that is the magnitude, on the y-axis. The discrete Fourier transform gives us the discrete frequency representation of the original signal. These are the discrete points. It has been joined by a thin line to show the trend. However, note that there is no continuity in the signal. This is also a sequence of discrete points. For example, the minimum value of the magnitude x of k occurs for a discrete frequency equals to 5. This is the discrete Fourier transform. One can also define the inverse discrete Fourier transform to recover the original discrete signal from the transformed signal. This is given by x of n equals 1 by capital N summation of n equals to 0 to capital N minus 1 into x of k multiplied by the basis function e to the power plus I 2 pi by n little nk. One can also understand the discrete Fourier transform as an expansion or representation of the discrete signal x of n as a sum of various components. These components are nothing but the discrete Fourier transform, which acts as an amplitude for the basis functions. This is the representation of a discrete function in terms of a set of discrete functions. Just like in Fourier series, we had discussed that any given continuous function can be represented by a linear combination or sum of various continuous functions which are sinusoidal in nature. This is essentially the discrete counterpart of the Fourier series. Thus, inverse discrete Fourier transform is the discrete version of Fourier series expansion. Now let us consider the various properties of discrete Fourier transform and fast Fourier transform algorithm. We denote D as the DFT operator. The DFT operator obeys linearity, which means that the discrete Fourier transform of sum of two discrete signals is equivalent to the sum of the discrete Fourier transform of the individual signals. This is in line with Laplace and Fourier transform's linearity property. Next is the periodicity. The discrete Fourier transform is n-periodic, which means that the discrete Fourier transform repeats after n points. where n is the number of points in the original dataset. Finally, we have the convolution property. The convolution property states that the discrete Fourier transform of two convoluted discrete signals x and y is equivalent to the multiplication of x and y in the transform domain. This convolution in the Fourier transformed space is nothing but the scalar product of the two vectors capital X and capital Y, which are discrete sequences of same size. Next, we look into the fast Fourier transform. The fast Fourier transform is an algorithm which is nothing but an optimized version of the numerical implementation of the discrete Fourier transform. If we try to implement the discrete Fourier transform as per its definition, it would take a lot of time and computational power. The Fourier transform in discrete version is optimized using the algorithm that is fast Fourier transform to reduce the number of calculations from order n square to order n log n. Order n square is the number of operations which one has to perform for direct definition-based computation of the DFT. Whereas implementing fast Fourier transform algorithm, the number of computations reduced to order n log n, which is much faster compared to order n square. To get a feel for it, let us consider n equals to 10,000. If we have n equals to 10,000, n square becomes 10 to the power 8. While n log n equals 10,000 multiplies logarithmic of 10,000, which is 10 to the power 4 multiplied by log n, which is 10 to the power 4 multiplied by 4, which is 40,000. Note that log of n is equal to 4. 40,000 is much less than 10 to the power 8 computations. Now, the FFT algorithm takes advantages of the symmetry and periodicity of the DFT definition and makes the number of operations much lower. In a nutshell, the FFT algorithm is shown here. Let us consider two signals x of 0 and x of 1. We have x of 0 equals little x of 0 plus little x of 1. This is the discrete Fourier transform. And the discrete Fourier transform at k equals to 1 equals x of 0 minus x of 1. You can verify this by implementing the calculation as shown here, where the total number of points capital N equals 2, and we have taken n equals 0 and 1 and k equals 0 and 1. So that is given in this diagram. There are only two components within the summation sign here. Now, this can be represented as capital X of n equals x of n plus minus 1 to the power n x of capital 1. Now, this can be represented in the general form as shown here, or diagrammatically shown here as a 2-point DFT, where x of 0 and x of 1 are mapped to capital X of 0 and capital X of 1, with these as the coefficients obtained from this expression. Now, the symmetry property of the mapping and the periodicity of the mapping is useful for defining the fast Fourier transform algorithm. The details of fast Fourier transform algorithm can be obtained in the references which have been given at the end of this lecture. These are the various versions of the algorithms for fast Fourier transform, which are one or the other way advantageous for depending on various applications. Now we move on to the geophysical applications of the various transform methods which we have discussed in the present lecture. The Laplace transform is used in seismic wave attenuation studies and diffusion studies. This is due to the fact that attenuation and diffusion involve decay or growth in time, which is appropriately modeled using Laplace transforms. The loss of energy as propagation through heterogeneous media occurs for the seismic waves is modeled using Laplace transforms. The Laplace transform simplifies the calculation of such wave attenuation and helps in the inversion of seismic data for obtaining the subsurface properties. The Z transform is useful in designing digital filters for applications in geophysical signals. Such geophysical applications range from seismic and acoustic waves. These waves are transformed into the Z domain, and then it becomes easier to apply a low pass or a high pass or any other filters in the discrete domain. This helps in enhancing the quality of the signal and remove noise. The discrete Fourier transform is highly useful in electromagnetic geophysical methods, such as the GPR. GPR stands for the ground penetrating radar. The time domain electromagnetic surveys also use the DFT or the discrete Fourier transform to analyze the frequency response of the subsurface. The DFT transform helps to transform the time domain electromagnetic signals into their frequency components. It helps to identify subsurface structural anomalies which are geologically very important. This can involve highly conductive regions or highly resistivity regions. This can include regions or geological structures having high or low anomalous conductivity. The fast Fourier transform, being an optimized algorithm of DFT, is also useful in such applications, which range from seismic waves, electromagnetic signals, and seismic noise. Nevertheless, FFT is also used in earthquakes, volcanic activity, and environmental change applications in geophysics. Thus, overall, we can say that these methods, which are mostly designed for analyzing discrete signals, are of paramount importance in various geophysical applications. Now, in conclusion, we can say that the geophysical datasets are primarily sample data, which are in the form of discrete datasets. This makes the use of discrete transforms more effective and appropriate. The discrete transforms also represent the data in discrete frequency form. This is more suitable for post-processing and further analysis using computers. One can have a look at the following references for more details on discrete transforms and the geophysical analysis. Thank you.